We have the four speakers, Keith Crook, Michael Knight, David Robinson and Alec Thomson. Michael has a history degree from Cambridge, so he's fit for anything. It says here David Robinson read maths at King's London. The other two went to respectively Nottingham and Glasgow, but they're rather shy of what they read. But you can't remember. Maybe they'll get reminded today. So Michael's going to start off. We look forward to hearing what you have to say. Thank you.
Am I switched on?
Yes.
Thank you. Ladies and gentlemen, thank you for coming. Don't think there's been one of these presentations on something concerning Emidec before.
Certainly they have.
And if you look through Resurrection, the 44 issues, there's one article in there from 1996 about Emidec by Ron Claydon that described EMI's first essay into computing, you might say, called CP407, a couple of which in due course went to British Motor Corporation, and that's the sum of it. Similarly, some of you will remember BCS of 50, that very fine conference, but in that busy agenda, Emidec found no place either, and not a single mention in that handsome booklet which delegates got. And it was really then that the idea arose that, well, we ought to do something about Emidec before we're all dead. And so that's why we call it a reminder. Now we're going to start with a film, a 20-minute promotional film made for EMI Electronics in 1961. In it we'll see and hear a certain amount about the 1100, rather less about the later and larger 2400, and also something of the way that early business and administrative applications were actually put onto those fairly early computers. In addition, I think it's a wonderful historical item, a little snapshot of Britain in the early 1960s before they swung. And, you may remember that was a time when a manager, by definition, had a secretary who fetched things and put them away neatly and took care of any keyboarding and worked the phone. So look out for that in the film. And afterwards, I'll give you a novice's tour of the Emidec 1100. After which, Dr. David Robinson, who was on the design team, will give us some more informed insights. Then Keith Crook, who was on the 2400 design team, will talk to us about that. And bracketed, for want of a better word, by Alan Thomson, who will talk about the involvement in all this of the NRDC, National Research and Development Council, and of Professor Strachey. And if we're all very quiet and hold hands, we might even get a glimpse of the ghostly 3400. So let's start with film.
just a big wooden box being delivered rather early on a quiet morning. A big wooden box, but inside it, the first of a new generation. Greater industrial productivity. More goods must be made, more must be sold. On this, our standard of living depends. But no matter how big our industrial installations are, or how modern our techniques, or how skilled our technicians and scientists, modern large-scale industry outdated administrative systems. The finest technical resources in the world can be frustrated and misused if our executives are confined within systems which developed under 19th century conditions. The development of the modern electronic computer has provided the instrument that can slice right through the paperwork bottleneck and allow management to concentrate on its decision-making functions. Just what can a computer do for management? There's been a great deal of theoretical talk, but let us see what a computer has actually done for Boots the chemist. We bought a computer to help us with the problem of supplying 1,300 branches scattered all over the country with the goods they need, and at the same time to keep stocks both in the branches and in our central warehouse down to a minimum. We carry a vast range of goods, and holding even a small percentage of unnecessary stocks is expensive both in the capital tied up and in the warehouse space that it occupies. Rapid distribution of merchandise on this scale is a gigantic physical operation. But controlling all this activity, there has to be an elaborate clerical procedure, the processing of orders as they arrive, and converting them into instructions for the warehouse, and into stock reports on which buyers and managers can make their decisions. In the photographic department alone, we offer the customer over 1,500 items. Working on this scale, a computer promised new possibilities of stock control and business planning. And so in 1960 we bought an Emidec 1100, and with the help of EMI staff we put it to work. This meant introducing a completely new set of procedures. Working with our new system on the computer, our branch staff make out daily orders and send them to the computer room at our headquarters in Nottingham. Special orders are written in coded form for goods for which there is only occasional demand. But orders for the standard lines are marked with a heavy graphite pencil on a special card. These graphite marks can be recognized by a sensing machine to which the cards are fed when they arrive. This machine acts rapidly and is able to handle 100 cards a minute. It functions by sensing the graphite in the penciled marks and punching a hole whenever a mark appears. The resulting punched card can be fed directly into the computer. The special orders are put onto punched tape, which can also be fed into the computer. Our first task each day is to feed into the tape reader the punched tape carrying the special orders. The computer is set in operation and begins with the sorting of orders. This is at 8:30 in the morning. The new system does not only mechanize isolated clerical tasks. Within this one program are integrated a wide range of operations which were previously handled separately in a variety of offices. The whole process is speeded up by the special ability of the Emidec computer to carry out several processes simultaneously on the same input of information. This provides considerable flexibility in our scheduling of the computer's daily timetable. 20 minutes after the first information is fed in, by 10 to 9, not only has the machine produced invoices and warehouse orders, but also a variety of stock reports and statistics.
One advantage of this system is that the invoice is printed out in warehouse bin sequence, so that the girls in the warehouse no longer have to walk about finding items that have been listed in random order. The rapid production of these invoices is invaluable to us, but the largest gains have come from the greater prospect of management control offered by the new exception stock reports. The buyer is able to know his stock position in more detail than ever before, but the reports he gets are not just mountains of figures. They consist of carefully selected information presented in a form which directs his expert attention where it is most needed. He now has an exact knowledge of the position in his warehouse, and he can ensure that no current line need ever go out of stock. He has this precise control over his merchandise because each day the computer notes which lines need immediate replacement and must be reordered. The computer also gives him clear warning when at the current rate of sales other lines will go out of stock unless he reorders. This kind of information allows him to plan his sales policy and his buying with an accuracy only possible in a computerized system. For ordinary clerical methods could never supply him with the necessary figures soon enough for him to act on them effectively. Our stock position has already improved since our buyers have had this closer picture of the daily pattern of sales at all our branches. And we're also finding that the computer offers new possibilities in our creative thinking about business operations.
This kind of successful computer application always follows a detailed and immensely valuable research study. In a very different setting, let us see what this involves by looking at another case history of a computer installation. British European Airways decided that their business was expanding so rapidly that a computer system must be introduced to deal with the ever-increasing quantity of revenue accounting. The existing accounting system was extensively mechanized, but even so it was inadequate to deal with the anticipated future scale of freight and passenger traffic. To see the type of skilled analysis that was involved in preparing a system for the computer, let us take one aspect of their problem, the accounting for the cargo carried in BEA aircraft.
Our cargo accounting is particularly complex. Everything from orchids to elephants passes through our sheds. Some of it is priority, some not. Some needs refrigeration, some keeping warm, some feeding. Some has special stowage problems because it's fragile. Some is radioactive and needs special containers. Some is too bulky to handle easily. This kind of diversity is only one of the factors our accounting system has to juggle with. By international agreement, all the information about cargo is recorded on a standard waybill. A package can be going to one of 1,000 different destinations and be carried in the space of a single journey by half a dozen different carriers, each of whom has to be paid for their part of the transaction. This kind of detail is all recorded on various documents, among them the waybill. We had a highly efficient clerical system operating smoothly, but the time was approaching when no human system could handle the increasing mass of work at sufficient speed. We decided to see if a computer would help. A member of our own organization and methods team, after discussions with EMI programmers, began the analysis of the existing system by learning from the departmental manager the procedure that a waybill went through after it arrived in our accounts department from the cargo sheds. The work of the individual clerks was studied to see how different procedures were carried out. Diagrammatic analyses of the way information flowed through the system was necessary to discover exactly what it was that the computer was required to do, what information came into the system, how it was processed, and what the end product was in terms of invoices, sales records, and other statistical reports. The whole existing system had to be analyzed in this way before work could begin on redesigning it to make use of a computer's special powers. The O&M team discovered that the system consisted of the feeding in of a great quantity of information, including that shown on the waybill, and then, as in many administrative patterns, the information was passed through a series of operations during which details were extracted and passed on into the relevant parts of the system. Finally, at the other end, invoices and other documents such as cargo sales reports and essential statistics were produced. The cargo system was only part of the overall pattern. Within this system, there were a number of separate operations, and the team analyzed these until they had broken each down into even more finely detailed stages. This type of refinement went on repeatedly until the point was reached where it was clear that the process could be reduced to simple, logical steps that could be handled by the computer. This kind of analysis requires infinite care. It involves a great deal of skilled thought by trained professional minds and the continual cooperation and active help of the departments concerned. The analysis showed that a major reorganization of many procedures would be necessary in order to make the most effective use of the computer. These changes were discussed with the chief accountant and other management officials. A report was prepared which described how the computer could be used and suggested the kind of impact that the changeover would have on the company. The report was accepted by management, and the next stage was to design a program by which the computer would carry out the work as required by the system. This needed further detailed analysis of the existing procedures before the writing of the actual program could begin. The organization and methods team worked with the programmers on the preparation of the complete program for the computer on a series of standard instruction sheets. Once the system had been programmed, there followed a series of trials on the computer itself. The results of these were checked in detail by all the BEA staff who had taken part in the plan. Although the simplicity of the Emidec code eases the programming problem, the size and complexity of the tasks meant that the team of programmers had to spend several months of constant effort before the first successful trial.
We have now seen how the computer can be put to work. But what range of problems can it tackle? Let us look at some successful applications. Today, computers are not only found in industry. The RAOC recently gave to the Emidec 2400 what is probably the biggest stock-keeping job in the world, helping the Corps keep the Army supplied with spare parts for all its motorized transport. Only a computer of the gigantic capacity of the 2400 could cope with the quantities of stores information at the necessary speed. It was a vast project involving units scattered all over the world, every conceivable type of vehicle, and a list of 220,000 spare parts. Just one of the problems is that military equipment is continually being modified. Therefore, the computer had to be programmed so that if asked for an outdated spare, it would automatically change this and order the correct spare part. And the correct spare part is very necessary when your transport is regularly given this kind of treatment. A project of this kind requires tremendously detailed programming. But for the Army, in time of crisis, only two things matter: speed and accuracy. And the Emidec 2400 can provide these in a way that would be quite impossible for the biggest and most efficient human clerical organization. Now for a very different example. Barclays Bank in London is using an Emidec 1100 computer to handle its bookkeeping for many thousands of accounts from 15 West End branches. Their business in these branches must expand greatly in the next 10 years. But they have been already finding it impossible to get sufficient high-quality clerical staff, and in many branches there was the additional problem of sheer lack of space. If they had the staff, there wouldn't have been room for them to sit down. For the usually conservative bank, great changes have taken place. Stopgap measures were no solution. Complete reorganization was necessary. With the computer system in operation, all the routine bookkeeping has been taken out of the branches. Instead, the considerably smaller staff handle transactions, and all the movements in every account are sent through by telex 3 times each day to a central computer. In the bank's central computer room, the telex messages are translated into computer language on punch tape. The computer can then handle all the bookkeeping previously dealt with in the separate branches, and the results can be sent back, again by telex, in a matter of minutes. The branch manager is now relieved of the drudgery of bookkeeping and routine office supervision. He still has the information he needs, and he gets it earlier than he did under the old system. The British Motor Corporation offers an interesting example of the successful application of a computer to a large-scale industrial project. For together with EMI, they have pioneered in computer applications with two EMI machines. The first machine has been in use for some time for processing their payroll. It now handles 20,000 weekly payslips. The latest machine, an Emidec 1100, is used for the preparation of dealers' invoices and for some information used in production planning. For BMC, production planning is not a simple matter. They are the biggest vehicle manufacturers in Europe, and 50 different models are produced, many on the same production lines. They are not produced in series. Vehicles on production lines at any one time differ from one another, and for each of these there can be a number of permutations of colors and fitments. From dealers' orders, the computer analyzes a printed list of specifications for individual vehicles. And this is used by the different planning departments which are responsible for the whole assembly, in which there are such variations as the tires to be fitted, the kind of headlights and winkers, the color and material of the upholstery, whether the car is to be left or right-hand drive, and even whether it should have wing mirrors. This room is the nerve center which controls all the stages of car production. To help in the actual assembly, the computer prints a production body card showing all the special features of each particular car that is to be produced. This card is attached to the appropriate body at an early stage of its journey as a guide to ensure that the right parts are assembled in each individual vehicle. BMC now have two EMI computers in successful operation. It is planned that in the future, detailed production planning involving such factors as the availability of stocks and raw materials will be able to be controlled by a computer. Meanwhile, the existing applications are working smoothly, helping maintain the steady flow of vehicles from the production lines. It needs highly trained specialists to put a computer to work, for although Emidec can take on giant tasks with seemingly magical ease, like all computers, it is only a passive instrument and needs human agency to set it in action. Courses like this are held regularly at EMI to explain basic computer procedures and to introduce the Emidec to those interested in the machine. The Emidec is unusually easy to program. People starting with a knowledge of their own organization's procedures can learn to program them in only 3 weeks. The lecturers are not theoreticians, but working programmers who spend most of the time dealing with practical problems of computer application. At EMI, we are in a particularly strong position to give instruction of this kind, because our computers are not in the experimental stage, but are tried and proven, and we have had the experience of many successful applications which we can now pass on to new customers. What we are selling is not just a machine, but a tried, computerized system, and one that works. We do not consider that our job has ended when we have produced and sold a computer. We believe our responsibility continues until it is satisfactorily doing the job for which it was bought. The students are shown the working of the computer, but the course is not a technical one. Most managements do not need to know how it works. This they leave to their technicians. All they want to know is what the computer is capable of doing for them. And they need to be sure that it is of sound design and will prove reliable in operation. The Emidec 1100 is proving to be exceptionally reliable, and there is the further reassurance that it was designed and constructed by the firm that has been the leader of electronic research since the early 30s. The cameras for the world's first high-definition television service were invented and made in our factory at Hayes. Today, we are still leading the research in the latest television development, color television. Studio tests are now wholly successful, and many uses for closed-circuit color television have been found. The color rendering has been accurate enough for surgical demonstrations. When a natural color television service is wanted, the equipment will be ready. electronic research is very wide, and all the resources of our organization and the experience of our scientists and technicians have been behind the development of our computers and of the parallel development of automatic machine tools. So for us, the design and production of electronic computers was a natural development in a field which we know well. We have now designed an extensible computer which can easily be tailored to individual and changing needs by the addition of extra tape decks and drum stores which increase the capacity of the basic machine. We also have had practical experience in building and installing a whole generation of computers which are now working for their living. We do not have to theorize about what a computer will be able to do. We can show what our computers are doing now. We can show how a wide variety of organizations have found that Emidec computers provide management with a tool of immense potentiality and great reliability. Such contrasting organizations as ICI and the Ministry of Labour, Sainsbury's and the Air Ministry have decided to use this tool even when it means breaking with traditional methods. To do this is no longer a leap in the dark. Others have led the way. There is a tried-proven tool available, ready to go anywhere in the world. It remains for management to use it.
Earning a living, I noticed that computer companies were hiring quite a lot of arts graduates, chiefly as trainee programmers. I didn't know what a computer was, but such enterprises couldn't be ignored, I felt, so I applied. IBM, I remember, decided on reflection they didn't need me. Might have been the wrong coloured shirt, I'm not sure. But I did get offers from Leo and EMI. And since EMI was actually offering £25 a year extra salary, 725 in fact, the choice was obvious. So there I found myself with digs in Southall, my very own Crook card, which I never got the hang of, I must say, at Dawley Road in Hayes, and quickly on to a 3-week course, which you glimpsed in the film. I was one of at least half a dozen, probably nearer 10, new arts graduate trainees at that time. And I think we all went on, initially at least, the 1100. My feeling was that for simple people such as myself and the others at that time, of course computer science degrees hadn't been invented, that's why we were there in the first place. The 1100 was a gentle introduction into the world of computing. It was straightforward by and large and readily intelligible. So let's start by having a look at the central processor unit. The working memory to hold immediate data and of course elements of the programs to process them was ferrite core, 1024 36-bit words, no more, no less. There wasn't a choice. At the bottom end of that array of memory were 16 special registers, including a couple of modifiers, or as I later got to call them, index registers, and register 16, which we'll come back to in a moment, which was rather important. The other special registers included common constants that are hardwired in. The instruction repertoire consisted of 31 functions, so-called, or 32 if you count function naught, which was stop. those functions were readily assimilated. They covered everything. There were your 4 arithmetic functions, moves, shifts, logical functions, and input-output, all the input-output. So one instruction would be a read, function 15 if I recall, 16 write. And you'd need to specify what device you were talking about, of course. We'll look at those later. But basically one program instruction in one word defined an input-output task. There was none of this requirement for a whole mass of different parameters to specify the details, as was the case on later machines, because there wasn't that choice. You want to read tape, you get one block, 198 character block. The other nice thing for us simple arts people was it was to address, so that was easily assimilated. Add A to B, that's not too difficult. A little bit more awkward was the fact that, I think unusually, certainly in my subsequent experience, it was 2's complement binary arithmetic rather than 1's complement. So that meant a row of noughts in a word was 0, but a row of 1's in a word was -0. Add time was an awesome 140 microseconds, so nearly 7,000 instructions a second, albeit a lot of the functions took rather more cycles than that. One interesting feature was that there was hardware conversion of binary to decimal and vice versa. Even more impressive to simple folk like myself was the fact that you had sterling conversion to and from. Back in the days when maybe not farthings, but halfpennies still mattered. So I thought that was very impressive, even more so when subsequently on different machines I actually had to program such conversion routines efficiently. Move on. Now, to back up this memory, there were up to 4 drum units of modest capability. As you can see there, those were developed and manufactured by EMI Electronics, and they were used for basic data requirements for the applications, and of course program storage, because programs were almost always necessarily written in well, segments, overlays, call them what you will. They got called all sorts of things eventually. Now, without contradicting what I said earlier, there was an option to have 4K words of core store. But from the point of view of program accessibility, only one of those still was accessible by program. The other 3K were used not as a drum cache, but as a kind of very fast pseudo-drum area to hold frequently used data which you couldn't fit in a working 1K. And in effect, for addressing purposes and accessing purposes, you again use the input and output instructions, and that expanded core store occupied or replaced effectively the first few tracks of drum 0. The only installation I'm aware of which took that option, that's not to say there weren't others, but the only one I can think of is BEA at Rislip. If we move on to talk about the console, you saw it there looking like a steel upright piano in the film several times. The interesting thing about it, with hindsight, is that there was no keyboard, there was no printer. And this is what brings us back to register 16. You can see at the bottom there 2 rows of lamps and switches. You can't count them, but in fact each row is 36, not surprisingly, and one of those represents register 16. This was a basic means of communication between the computer and its operator. So you would determine options for the program by setting switches in register 16. Register 16 would also tell you state I of the application as appropriate. Above those, you notice, in particular, there are 2 screens. These are oscilloscopes, in fact. And each one independently was capable of displaying the contents of 32, 36-bit words, either of memory or of a selected half track of drum. And the nature of the display was that binary zeros were faint dots in a row, binary ones were bright dots in a row. I once spoiled a night's commissioning of, I think it was a BA machine actually, by fiddling with the switches under those screens. One of the tedious cycles of tests, I remember, was a core memory test, which worked by spreading a pattern of noughts and ones, which apparently the memory had difficulty in holding, right across the memory. And to relieve the tedium, you know, you could just practice your binary finger work on those switches and see this pattern of noughts and ones spreading through the memory. Apparently that caused extra stress and strain on the actual core memory by some arcane process, as it was explained to me by an engineer when the machine had stopped. And so I didn't do it anymore. On the right-hand side there particularly are various displays and knobs which I couldn't explain to you because they were for engineers. And it was explained carefully on the course I mentioned that trainees in particular, programmers in general even, didn't go near that side of the console because lightning would strike them. Now this is quite simply a list of the peripheral equipment, standard peripheral equipment available on the 1100, and it was fairly typical for the time, so I'm not going to dwell on them in detail. One of my favourites was in fact the old Samastronic printer. You saw a glimpse of that in the film without maybe realising it. Interesting because it had 2 independent paper webs, a wide one and a thin one, and also I recall the primary method of repair by an engineer obviously was to strike it in various places with a hammer, a rubber hammer admittedly, or sometimes a shoe served. Most interesting probably was the magnetic tape units. I don't think any Emidec 1100 was ever shipped without them, and normally you have a minimum of 4. And these were used as the basic medium for storing files. Now I mentioned earlier that 1996 article on the 407 of EMI, and I have seen it suggested that that might have been the first computer actually to exploit magnetic tape for file storage. Anyway, it was taken as read as far as the 1100 was concerned. Magnetic tape files were held in fixed length blocks, as I've said, on American Ampex tape decks, being scared to death one day early on in my EMI career, because I didn't quite get I should explain that the start-stop mechanism was assisted by having chambers, semi-vacuum chambers on either side of the spools, which had loops of tape in them to absorb the start-stop shocks. And on one occasion, never to be forgotten, I failed quite to get together the male-female plastic connectors of the trailer, of the leader rather, and the reel of tape. So when I switched it on, everything disappeared into the vacuum chambers, and there was a hideous, loud roaring noise. And I was greatly perturbed, mindful of what my salary was at the time. I had been told that each one of these tape decks alone cost £5,000, which was a worrying thing to have irredeemably broken. Needless to say, it wasn't such a tragedy after all. The other interesting thing here is that there are offline functions which could be carried out to transfer cards to paper to magnetic tape, or print files from tape to printer. That's rather analogous to what, say, later on I found 1107, Emidec 1107 doing by software, where one of its executives was called Exec 2, and it only ran one application main program at a time, but it had things called symbionts, which did by software what the Emidec 1100 did by hardware. Now here's I'll call it fairly complete list of Emidec 1100 customers. Oh, I beg your pardon, I should say something about programming and software first, shouldn't I? I haven't got a slide for that because there isn't much to say. Coding, of course, in those days was done on coding pads, one instruction per line, which were then punched onto cards, 3 instructions per card. And the coding was, there was no assembler, let alone higher level languages. So it was machine coding, but it was relocatable. So you didn't have to work out absolute addressing of everything as you wrote it. A program known as synthesis would do this for you and produce absolute address object code from what you coded. Beyond that, of course, there was a trace facility for program testing. And incidentally, on the console, there was a means whereby you could regulate the speed of instruction execution from one at a time to one every few seconds to 50 a minute, and so on and so on, which was quite a useful program testing. And of course we had memory dumps available in octal, which you soon got used to deciphering. And there was a standard magnetic tape sort, very important for a tape-based data processing machine. And by, there are a few sort of utility subroutines and macros produced, as I recall, but basically very little in the way of software at that time. One of the consequences was that when you came off this 3-week course, incidentally, of course you were by no means experienced, at least let alone expert, but you were actually already a bit useful, because somebody would bring you a specification of what all or part of an application had to do, whether it was payroll or production control or who knows what, didn't matter, because all you had to do was turn the specification into program logic, which of course you flowcharted, and just this very afternoon I've been handed a memento of those days. Remember the And then you coded it and tested it, and you've done something valuable. Now, those are pretty blue chip customers, I think you'll agree, certainly for those days. But of course they needed to be. The typical sale price of a 1100 was about £250,000 in old money. BEAs again, with 8 tape decks, and the expanded memory was might have been the biggest of them all, and the most expensive, at around £300,000. Now, to get a sort of comparable figure today, of course, you need to multiply that by certainly 15, perhaps 20 times. And then you have to bear in mind that the customer would need to make a comparable investment in the power supply and air conditioning requirements of the installation. So a lot of money for a fairly new, iffy sort of area of business. And a part of the problem was that in 1962, new orders didn't seem to be coming in. So we trainees had to amuse ourselves quite a bit. A lot of reading in magazines got done. Computer magazines, obviously. Datamation was my favourite. We would program things for ourselves. We would read anything which crossed our path. I couldn't get my head around an algol manual I came across. But I think they were planning an algol compiler for 2400. I even came across an IPL5 list processing language manual, which may point us in the direction of Christopher Strachey, I don't know. So things were getting a bit desperate, and I was, for one, was getting a little bit alarmed because his father was constantly telling me the world doesn't owe you a living, boy. Well, I was getting a reasonable living, but I certainly wasn't earning it. So I got a job with Emidec. And consequently, one summer morning, I blagged my way past the dragon who looked after manager Bert Pitt's office and nervously explained my treachery to him, to which he reacted with its astonishing calm. And later that day, we all got convened into a suitably large space there in Hayes, Dawley 1, and somebody important, it might have been Norman Hill, I'm not sure to be honest, announced that EMI's computer division was being taken over by arch rival ICT, to the astonishment of practically everybody there. And so chronologically, that's more or less the end of the Emidec story. However, it's far from the end of our presentations today, and so I'd like to pass you now for some more insightful thoughts about the 1100 to Dr. David Robinson.
Good. Well, thank you very much for inviting me. It's the first time I've been to any meeting of the Computer Conservation Society. And it's a very interesting commitment which you have. Firstly, I would like to correct one little detail. I'm not actually Dr. Robinson, I'm Mr. Much as I would like to have been Dr. Robinson, it never actually happened. Just a bit about myself. I joined EMI in 1955 after having done 2 years national service. And EMI took me on as an engineer, largely on the strength of a degree in mathematics, an interest in anything which could do arithmetic, and the fact that I knew Ohm's law. I also had a copy of the Royal Signals Handbook of Telecommunications, a thick blue volume, which I think my children abstracted later. But I'd always wanted to work on computers ever since I'd read about goings-on in the USA and NPL while I was still at school, things like the ENIAC and EDSAC and things of that sort, fascinated me. And I also have a family connection with EMI, so I think that's how I got the interview. Anyway, at the time I joined EMI in 1955, EMI had got this contract to produce what was referred to as, I think, CP407, a machine to produce payroll calculations for British Motor Corporation. And this was a valve machine. It was a serial valve machine. They tested their basic concepts, building a pilot machine first, just to get the circuits right. And then they went on to build this valve machine. There were thousands of valves in this thing, and the voltages they used were from -300 to +300. And the heat it gave off was absolutely awesome. We needed great big fans to keep the whole caboodle cool and working. And of course, the -300 +300 was quite a challenge. And you could always tell who was an engineer, a true engineer, because he always worked with one hand in his pocket. The thing being that you got this across your fingers, you would survive. If you got it across your body, you wouldn't. Anyway, this machine, as I think somebody said, previous speaker said, was possibly the first machine to use magnetic tape as storage between runs. And having designed the basic idea of the valve machine, they then thought, oh, we need magnetic tapes. What are we going to do about that? And we got somebody called Godfrey Hounsfield in as an engineer who was going to deal with magnetic tapes. Now, how do I make this thing work? There we are. There he is. Now, I think most of you by now have heard of Godfrey Hounsfield. How many people have heard? Exactly. Most of you. He later became Sir Godfrey Hounsfield, FRS, and a Nobel Prize winner for his work on developing the brain scanner, to which many people owe their lives, including my own wife. So I've always got a very soft spot in the memory of Godfrey. But all that was in the future. His future, not mine. I never worked with him on the brain scanner, otherwise I might have ended up a little bit better than that. Anyway, when I first joined EMI, with my degree in mathematics, they said, they gave me a corner in an office, they gave me a T-square and a drawing board and a pencil. No, it didn't be a pencil, I provided my own pencil. And they said, that machine needs to be able to multiply, and that machine needs to be able to divide, sorted. And so I designed a multiplier and a divider. I was effectively straight off the street. You can't imagine anybody these days being given a job in the computer industry and being told to design a multiplication and division function for, admittedly, a serial machine. But there you are. These days you need a degree in computer science before you get through the door. Anyway, that's how Godfrey Hounsfield came in on the act. We just knew him as H. We didn't even call him Godfrey, he was H. That's how we knew him. Now, in doing these magnetic tapes, Godfrey decided he was going to use transistors. Transistors in the late 1950s were newfangled, and most electronic engineers didn't trust them at all, and certainly Ron Clayton, whose name has been mentioned this afternoon, certainly didn't really trust them. But Godfrey was strong-willed, and the magnetic tapes were transistor-based. And having made transistors work for this, Godfrey then thought, well, we actually had a group of people who thought, well, what are we going to do next after the 407's out of the way? Let's see if we can make a transistor-based machine. And we had a design team which consisted of somebody called Bob Froggatt. You remember Bob Froggatt? No. And myself, principally, did the brainstorming and decided that one actually do logic using transistors and core and magnetic ferrite cores. So let's put our next. I got the right one. Yes, there we go. Now these are the basic elements which we decided we would use for our new computer. Firstly, a ferrite core. Now, as you know, ferrite cores used normally in computer storage, you can magnetize them one way or you can magnetize them the other. They're permanent magnetization, clockwise or anti-clockwise, if you like, with the diagram there. And you need a certain amount of ampere turns to make them change their direction of magnetization. Give them less than what they need and they won't even move at all. So give them enough ampere turns and they'll flick over their direction of magnetization. So to make them work, you could either have so many turns which would be enough to turn the core over directly, or you could have windings with half the number of turns, which with current going through any one winding would not be enough to turn the core over, but with winding going through with the current going through two of the windings, it will be enough to reverse the direction of the core. Well, fine, that was great, but of course we don't know which direction the core is magnetized in just by looking at it, and the only way you can find which way the core is magnetized is by trying to unmagnetize it or reverse the magnetization again and seeing whether you get a pulse of current out of an output winding. So we then have an output winding which goes into the base of the transistor. We use OC72s, I don't even know whether you can buy them these days. And when you've got the pulse of current up there saying the core reversed its direction, then you've got a pulse of current down here which could then go on and feed the windings on other cores further down the logical chain. And this way you could build almost any sort of logic you liked. But you did have to drive the core continually with a clock pulse. So we had a 100 kc clock pulse permanently trying to unmagnetize the core, reverse magnetize the core. And then if it had been set by one of these windings, or maybe by a pair of half windings, then the next clock pulse that comes along, you get an output into the transistor. If the core hadn't been set, then you wouldn't get an output. And so that way, you've got a basic logical gate. And of course, by sending the current around one of these windings in the reverse direction, you could have an inhibit as well. So if you had one trying to set the core and one trying to not set the core, the one would cancel the other. So you've got the basic 2-gate and the basic inhibit. Now we represented this in a logical fashion this way. This was the sort of notation we used in our diagrams. Basically the core, a clock pulse coming in, a current which would set it, half sets, maybe an inhibit, a variety of combination of windings on the core. Not all done the same way, it depended what we wanted that particular core unit to do. But one thing you could do is if you took the output from your transistor, you could use it to reset the core. So the clock pulse would come along, clear the core, or set it to the naught state if you like, but in doing so that would produce a pulse of current out here through the transistor, and because of the phasing, the pulse here would last long enough to set the core again. And that way, if the core was set to start with permanent clock pulse going in, the core would remain giving pulses, tick, 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 giving out pulses until some other an inhibit line like that came and turned the core off and stopped it. So that way you've got a logical trigger or a bistable device. It was a feature of the OC72, which is a very early germanium junction transistor. But if you drove a lot of current into its base, and then the current stopped, the transistor would remain conducting. You got what was called, I think, minority carrier storage, or hole storage, or holes which carry the current, wouldn't dissipate immediately. And so the transistor would go on conducting a little bit longer. And we had this capacitor to make sure it did. And then we had another signal going in there from another clock pulse, a bit out of phase with that one, which would then turn the transistor off. So if we go and look at our next picture, there you can see the 100 kilohertz clock pulse going in, and this is sort of signal which came out, and since the output signal overlapped the clock pulse, the bistable would keep setting itself. Now, Bob Froggatt and I worked away for quite some while on this, and we thought we could build a nice small computer, something really small. In fact, when we talked about it casually amongst ourselves, we referred to this thing as OXO, something which could be small and got into a fairly manageable sized cube. You've already seen pictures of the ultimate result, so the idea of getting it into a small space, I'm afraid, was tested to failure. It occupied the whole room. Now, I've described basic logical element. But your reaction is probably going to be, hey, this is okay as a logical element, but it's kind of slow, because it's going to take one clock pulse, and the clock pulse is 100 kilohertz, it's going to take 10 microseconds to do any kind of, before you get any kind of result out of it. So this is going to lead to a pretty slow old logic. Well, you have to remember, firstly, that we had come from a serial machine background. The CP407, which is the first thing we worked on, was the valve machine, had a clock pulse of 100 kilohertz. And so it took 36 clock pulses for any one word to trundle by. So if that's the kind of standard you're coming from, the word takes 360 microseconds to wander past any particular point where you're looking at it. This seemed fast. But there is, I have to say, one area in a computer where this kind of logic just is a non-starter, and that is if you're trying to add numbers together. If you've got an accumulator where you want to add binary numbers, so you're adding in parallel, you're taking your whole 36 bits held in an accumulator, and you want to add your next whole 36 bits in clunk like that. There is the problem of the carries, which have to trickle along from the least significant to the most significant digit, and in the worst possible case, if you've got a row of ones, well, by the way, I must take it to you the last speaker. A row of ones was -1 on the Emidec 1100, not 0. It was on the 1107, which I also worked on, the Univac machines, where -0 and +0, -0 is a row of ones and +0 is a row of noughts. That was the twos complement machines, or ones complement, or whatever you call it. In your adder, you've got to pass, in the worst case, a carry through 36 ones, please, reasonably fast. Please. So, and what we did in that case, we let the output from one output from one core, go through a transistor, and I think it was a slightly beefier transistor, and it immediately became the clock pulse on the next core. So when one core was turned over, the output immediately turned the next one over if it contained 1. And that turned the next one if it contained 1. And that way you could get your carry progression across the whole width of your accumulator. And we reckon we were doing quite well. I think we got about 180 nanoseconds. The first time I've ever come across a nanosecond. 180 nanoseconds per stage, which meant, when you work it out, you could just about get the carry right way down the width of the 36-bit accumulator in the space of one clock pulse. So we had to tweak the little sort of logic quite a bit to make it work. So I'm going to show you now a basic schematic of the machine. How's my time over? Yes. These are the actual elements themselves. I'm indebted to somebody called Andrew Wiley. I don't see here. I think he said he couldn't come this afternoon. For these two pictures, the right-hand one is one of the circuit boards of an 1100. And you can see the cores mounted here. And here is an enlarged picture of one core. And you can see how small the cores were. They were 80 mils, that's 0.08 of an inch, 2 millimeters just about across. Really quite small. And of course they had to be wound by hand. There's no way you could do that by machine. And so we had two girls sitting in the corner of the office under the window in their own little room. Tracy and Mildred, I think they were, but I'm not absolutely certain what their names were. I can't remember now. Who spent their life stuffing 38 gauge wire through these cores and putting the right number of turns on according to the specification. And when they had made the core like that, we had various ways of potting them. Sometimes in silicone grease, sometimes in epoxy resin, sometimes just left naked like that, but we didn't like leaving them naked, a bit vulnerable. There were various ways. But they're the resistors, and these are, no, I think the silver ones are the transistors, the OC72s, and there are some diodes there as well. You don't often see components of that size these days. Moving on. Right, the basic schematic of the machine itself, as the previous speaker told you, it's a two-address machine. You added A to B. The fundamental design of the machine was one address. You had your memory, you had an accumulator, which I've just described, could add or subtract 36-bit words in parallel. We had a shift register to one side of it, which could shift cyclically round through the accumulator, either leftwards or rightwards. We had an address selector here which would drive the memory. A register up here would hold, we called it the write register, which held a word ready to plot back into the core memory. Of course, remember, when you read from a core store, it's destructive. So having read the word out, you've got to put it back again. This is fundamental. It's part of the baggage you have to do. So when you read something from there, it automatically went round and all the way back through the write register and was blocked back into the same place that it came from. There was an instruction store which held the 36-bit instruction. There were 2 bits at the left, 3 bits at the left-hand end which contained an address modifier, which was the address of one of the 7 modifier registers in there, which could be added to the instruction before it was obeyed. So you got address modification. 2 10-bit addresses, digit 8 to 17, digit 18 to 27, 2 addresses, and then the rest of the instruction was taken up with various odds and ends, like the number of shifts you were going to do or which channel you were going to do the output to and things of that sort. I haven't shown the drums or any of the peripherals on here. The drums are over here somewhere, and the peripherals are over here somewhere. But I felt I was confined to one diagram, so I thought I could stick with what I call the CPU. When I described this, I had lunch with Chris Strachey once. Chris Strachey's name's already been mentioned once this afternoon. I think he was a government computer expert, wasn't he? Anyway, I took him out to lunch one day when this was all being invented, And he said to me, David, I think maybe Mr. Robinson, when you designed it like that, why don't you leave it as a one-address machine? Gives you a great deal more flexibility because you can have bigger addresses, more memory. If you've got a two-address machine, you're really locked into that 1024 word memory because it's 10 bits for the source address, 10 bits for the destination address. And if you want to keep 1 or 2 other bits over there, you ain't got room in your address structure or your instruction structure to admit a bigger store. But again, you have to remember, when we invented this machine, 1,024 words is more than anybody else in the market have got. And as already been said, we went to 4,096 words. We really cheated because the last 3,000 words were really address-wise, operationally drum store, but they were fast. With that, you've got your whole machine. If you want to multiply, for example, you put your multiply in the shift register there. Your multi-can stayed in the general purpose register here. And then what you did was you looked at the last bits here and decided whether you're going to add that into there or whether you weren't. And if it was a 1, you added it in. Then you shift the whole lot one place to the right. Look at the right-hand bit here again. Add this again, or don't, into the accumulator, and so on. And of course, as the process goes on, your answer extends across into here. You end up with a double-length word in accumulator and shift register. But you're only doing the arithmetic on the 36-bit left-hand part. And the division was similar, somewhat more complicated, particularly since we had to cope with negative numbers. We had to cope with negative multiplier, negative divisors, negative dividends, positive and negative multiplicans, positive and negative multipliers. And so we had a few dodges for coping with that. I think at this point I'd like to say a little bit more. How do you make all this work? Well, each of these devices were controlled, and I haven't shown them on the diagram, by control lines. They were single signals which went in, down which, if you sent a pulse down this line, it would prod that particular thing into action. So one control line would say shift the accumulation shift register one place to the right. Another one would say shift it to the left. Another one would say gate the A address from here into the address store. Another line would say get the word in there corresponding to the address we've just put in there, and so on. There were in total about 80 of these control lines. And with those 80 control lines at your disposal, by sending the right signals down right ones at the right time, maybe 2 or 3, maybe something you had to pulse simultaneously, the whole caboodle would work. The trouble is you had to sit effectively, it's a bit like sitting at the keyboard, pushing the right keys. Well, you needed something which would do it faster than that. So what we had was what we called the control matrix. Got it. This was, I think, my idea. We have a shift register there, which, once you started going, would send a pulse of current successively up there, up there, up there, up there, up there, and so on. I think there were about 20 stages. And that pulse of current would then go up through these cores here, which are threaded on. And of course, if any one of those cores was set, then an output pulse would appear along the output line. So if you wanted to operate a certain set of these control lines, the 80 control lines I've mentioned, by passing a pulse of, first the pulse of current down what I've shown is this red line, through the selected cores to set them, and then you send a signal going along here, which goes tick, 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 tick along there. Whenever it found the core which was set, it would be inverted, it would be reversed, and the signal would come out along one of these, or more than one of these. And so, for each of our functions, we had one of those wiggly red lines, which we called laces. So we had to put these laces, we had to thread these laces through this matrix in the right way to make the computer do what we wanted. One lace effectively for each instruction, the instruction set. Now, actually, it was a smidgen more complicated than that. We didn't have 32 laces. We actually allowed ourselves 128. And I'm just going to go back to the previous. How's our time?
We're overrun.
Am I? By how much?
We're already overrun.
Okay, I'm very nearly what we had was the 35th digit from the accumulator also making an extra bit in the instruction. So that way we could choose, depending on whether something was negative or positive, we could choose whether we should lit fire one of these lines or a different one, and therefore we could make the machine work in different ways depending on the output of the instruction, depending on the output of the arithmetic value. One more picture and then I'm finished. How does one build a matrix like that? Well, we put the ferrite cores into a sandwich, a perspex sandwich. Because they're very fragile, these things. So we sandwiched it between 3 layers of perspex. There's our core, it's edgewise on. And then you put as many wires through as you liked, and you knew you wouldn't break the core. You pull the wire as tight as you wanted, and it always avoided the core. So that was the inner workings of the 1100. There's more which I could say, but I'll stop at that point. Unless
do you hear me? So we just heard about the Emidec 1100. That was a commercial computer development by EMI. Now there were initiatives outside of EMI which led to the next machine, the Emidec 2400. So I'll say a little about the initiatives from the NRDC before Keith goes on and tells us about the computer. So I'm going to tell you a little bit about the overall history of the time. After Keith has told us about the 2400, I'll then say a bit more about what the NRDC did next for the 3400. So about the NRDC. The NRDC was set up as a government body in 1949 to encourage, and its basic motivation was to encourage the use of patents held by government bodies. It's at that time there were a lot of research institutes and universities that held patents. In terms of reference of NRDC were to provide exploitation of the products by British industry and do that by means of development grants and recover the costs from patent licensing. Lord Halsbury was appointed as the managing director. He got interested in putting to use some of the early computer patents that were held by the NRDC, particularly the Williams storage tube from Manchester. And he recruited Christopher Strachey. Strachey at that time had a high reputation for his programming work on the Mark I computer at Manchester, and Strachey joined the NRDC in early '52. He became a key advisor to Halsbury on computer developments, and he came to have great influence within the NRDC. So Halsbury and the NRDC felt that the UK computer industry wasn't moving fast enough to develop computers for large-scale data processing and was lagging behind the American manufacturers. So they set up an NRDC initiative for a British large data processing system. The NRDC initiative enacted in 1954, and it had the aims of exploiting new technology, growing a viable UK manufacturing industry that would compete in large data processing systems with IBM. And the three new technologies we're considering were, well, we've heard about the transistor on the 1100, but there were more reliable transistors coming along. There was magnetic tape storage was improving, and magnetic tapes were improving. So, and they thought that we should have improved computer tape drives for large data storage. So NRDC wanted to sponsor development of a large data processing system, and they let a contract for development and manufacture. NRDC had sponsored development, earlier computer developments, and were working at that very time with Ferranti on Pegasus, but there have been some disagreements on the design and on the commercial arrangements. So when EMI made a proposal in 1955 for a computer they called a mass filing system, it was welcomed by the NRDC. The mass filing system proposal was from a different part of EMI. There was a part that was new to computers. It wasn't from the 1100 project. And the design was to be done with the NRDC. That meant with Strachey. And 75% of the development costs were to be recovered by a levy, which EMI had agreed that there would be a levy on all computer sales, all EMI computer sales. So NRDC gave EMI the go-ahead in October 55 for this large transistor-based EDP system. Contract was for 300,000 at the time, and the contract also included the development of a UK computer, a magnetic tape drive for computers developed in the UK. This became the 2400 project in EMI. And here's a description from the original brochure, which I guess you can read. It's basically saying it's an advanced data processing system to produce a system by 58 which would be well ahead of contemporary machines. So it was an ambitious project. And I think I'll just show you the illustration that was in that brochure, and then hand over to Keith to tell us about this machine.
Hello, my name is Keith Crook, and I was part of the design team for the central processing. I didn't conceal my degree. I was actually in Nottingham, and I got studying physics, and I got a first-class honours degree, which is probably why I was headhunted by this mad Russian called Charles Kranskoy, who actually led the team. The project manager, the project leader for the team, was a person of great intelligence called Norman Brown, who now has no interest in computers or whatever, as far as you know, but the overall supercomputer was a chap called Charles Kranskoy. And the best thing he ever did was to go to America and bring back the first ever record in this country with Tom Lehrer, which we all sat around in the office and played in 1956. And Tom Lehrer records weren't made in this country from 1959, so we were probably some of the first people in this country to hear this wonderful character, Tom Lehrer.
They were banned, weren't they?
No, I think they might have broadcast them on the wire. A bit like Maximum in fact. He also brought back another record by a lady called Ruth somebody. Decidedly raunchy, including titles like his popper doesn't pop up anymore, which referred to his toaster. That was also rather amusing. Anyway, Kranskoy got the money and ran it all, and Norman got this team together, and I was headhunted from another part of EMI Electronics to come and join the team. Now, basically, we only ever made three. One you saw referred to in the film went to the Royal Army Ordnance Corps at Donington and Chilwell, about which we know very little. One went to Russia, about which we know nothing at all, and I suspect that COCOM didn't know much about it either at the time. We don't know what they did. Maybe it was just their way of buying into the computer business. You know, they could get ahead of the field quicker by buying something like that in. And I guess they thought there probably wasn't much future in going to IBM to buy one, so they bought one from us. And all we know about it is they dropped half of it in sea at Murmansk and came back and ordered another 3 replacement units. The main machine, that's quite true, yeah, we sent it all and then we had the letter back saying drop the search unit in the harbour at Murmansk, please send another search unit. The main one, the largest installation by far, was the Ministry of Pensions and National Insurance at Newcastle, which was replacing a card installation. And I'm just going to use that as the illustration because it had pretty well everything. And the whole principle, as Alan said in the introduction, the whole principle of system design of the 2400 was that it was going to be a data processing system. It was just going to process data. Nothing else. Wouldn't be involved in the bric-a-brac of life like changing the toilet roll. It was going to process data. So the central processor, there are a string of mag tapes down there. They went into and came out of there, and that was the system. Everything else was done by these surrounding peripheral units. There was an input unit which you could feed stuff, cards, tape, keyboards, whatever, onto these tapes, take stuff in, write it on the tapes, which would then be read into the computer. Newcastle, MD&I certainly didn't have one of those, and we don't know if Thomson did, but it may be a unit that we made which was never actually sold. Somebody here may know, I don't have it. This unit here, card reader punch, would take input from cards, because of course MD&I was a card installation, and the entire pensions information of the country would be on cards. Rather than stuffing into there, you put it into here, and it wrote to these magnetic tapes. And equally, when you wanted cards punched out, you took a tape off the mag tape, and you punched it out on here. There was a print unit which was connected to a couple of Xeronic printers. This was a very fast printer made by Xerox, which nowadays would be like a laser printer, but in those days the image that you wanted to print was projected on a cathode ray tube onto a drum. Drum went round, picked up paper, put electrons on the paper, picked up the dust, powder, that was fused on and came out, and the only problem it had was that if the paper stopped, it caught fire, because it had to heat this paper extremely hard. I didn't know anything about this unit at all, and I was going to ask people until somebody, one of my colleagues at EMI, told me today that I had a hand in designing this. That's the tape. He said, I did the tape bit and you did the printer bit, but I don't remember anything about it at all. I've made no apologies indeed for getting any of this wrong or forgetting bits, because it was over 50 years ago. There was also a file search unit into which you could put a series of keys on one tape and say, go away and find it. The reason you needed that originally was that we had, one of the concepts was a 4-inch tape drive. This was going to be used for archive, 4-inch wide tape, no vacuum chambers, no arms, it just sort of took off and went very slowly. And it had this archive, had 8 half-inch tracks on it, 4-inch tape, and you would go and look for stuff on this archive. This went quite well until we were about to give a demonstration. We had a little dolly bird in here who was a demonstrator, and somebody said, pick up that reel and put it on that hub, and she couldn't even pick it up. I mean, this reel weighed about 10, 15 kilograms, something like that. She had to pick it up, and she's not my height, so she's down, she's got to pick it up and get it on its substrate, and then thread it through. So that was the first objection, but in practice, MD&I said, no, we don't want that. We'll keep all our archives on a single magnetic tape. But this file search unit could read either 1-inch tapes or 4-inch tapes. So we had here the central processor with 4 tape buffers, and all these units here all had a magtape interface on them. They were all controlled by this switching unit, which was really just like a vast telephone switching system. It simply switched any of the 25 magnetic tapes here, which I'm going to describe later on incidentally, to any one of these 4 buffers, or the input unit, or the file search unit, or the print unit, or the card read punch unit. Now, There's a lovely description of 2400 in the film, when he called it the gigantic 2400. That's gigantic it was. Douglas Adams described at the beginning of Hitchhiker's Guide, you know, difficult to conceive how big the universe is. It is huge. It is unutterably huge. And I sometimes think of the 2400 as that. This is a bit of the NPNI 2400 installation, Newcastle. And it's only a bit. This part along here is that's the back. That bit up there is the back. So the whole of this lot here, this back row here, is the processing unit, central processor. This is probably the file search unit. You can't tell when they just pad up. Here's the operating console. Looks like something that came up out from Blackpool Tower, ballroom. There is one tape unit, of which there are 25. So somewhere else, there's another unit with 2 Xeronic printers attached to it, and a card tape converter, and a number of card readers, and a number of card punches. Big. Unlike what David was saying about 1100, it didn't actually generate a lot of heat. It set out to be, as Alan said, it set out to be an entirely transistorized system, totally solid state machine, and that's how it ended up. No valves in it at all. So it really didn't consume a lot of power, so there were no special requirements for air conditioning or anything other than the fact that, I suppose, because there was so much of it, it did use quite a lot of power. But nothing seriously heavy, I don't think. And there's another picture later on of this taken from a different angle, but to get the scope of it, you need to have you need a camera somewhere where it doesn't need it. But it was huge. And the field engineer on the site, there were several, but one of them was John Bradbury, who was going to give this talk today, except that he double booked his time. So that's the whole system. That just gives you a scale of how big it is compared with the 1100, which you saw in one room. I mean, this was in one room, but it was about the size of a football pitch. The mag tapes were very interesting. I didn't know, what I found most interesting about the 1100 presentation was I didn't realise they were 1-inch tapes. I thought they were half-inch tapes. We didn't have a lot of, although the 1100 was elsewhere in Dawley Road, in EMI, we were doing our 2400 bit, and I don't think our parts I never met anybody from the 1100 team, didn't know what they were doing. I knew that H. W. Hounsfield was something to do with it, and later in life I learned that he was something to do with that, as well as going on to do the other things he did. But I didn't know they'd got 1-inch tapes. I thought they had sort of, I was going to say standard half-inch tapes. Maybe half-inch wasn't the standard at that time. So these are the 1-inch tapes that we designed. And you've got standard 2400 foot reels. Here, you've got these things called scramble bins, which, as Mike Knight pointed out, the tape is gathered up in to buffer. You can't quickly move something of this mass, so you have to store the tape in a loose form inside these scramble bins. Then they come out over these capstans, that one there and that one there, and the head is in between. And this was run out of contact with the heads. Most half-inch tapes now, all half-inch tapes thereafter were run in contact. This run out of contact. Therefore, in order to get data rate, because you're that much further from the head, you have to move the tape extremely fast, namely 200 inches a second, which is quite fast, and it is spectacular when it goes wrong. Absolutely spectacular. Imagine these scramble bins filling up 200 inches a second, and the detection mechanism says the scramble bin's getting a bit, get a bit forward before you know where you are. As John Bradbury said in his notes, an undocumented feature of the mag tape units was the ability to turn a foot of 1-inch tape into 4 feet of quarter-inch tape. But I never saw that, but when it went wrong, it was pretty spectacular. But they were very good. So these were the characteristics of the tape. It was 1 inch wide on 2400 foot reels, around 200 inches a second, and the way that it worked was that if you remember, there were these two capstans. The tape was lying across those, waiting for something to happen. When you wanted to go forward, you applied suction on this capstan, and it just drag the tape along there. If you wanted to go backwards, you applied suction on this one and it grabbed a hold of the tape and pulled it the other way. And the head was in between the two capstans. All very simple, and it worked. And the data rate was 20,000 characters a second. The 1-inch tape was actually had 24 heads on it, so there were 24 tracks on this 1-inch tape. And essentially, they were 2 half-inch tapes, and you could read and write in both directions. So you could imagine, the easiest way to imagine it is you've got a half-inch tape going that way, then you get to the other end and you've got another half-inch coming back. So each half of the tape had 12 tracks, of which there were 6 data tracks, 2 clock tracks, 1 parity check track, and then there were 3 correction bits. And those 3 correction bits enabled you to do single error correction, so you could actually correct single error on the tape by means of these 3 extra bits, and you could detect double errors. So it was a pretty good system. And you could also write control points on the tape. So you could say to the tape unit, or the search unit, or whatever, take tape number 30, tape unit number 21 and move it to control point 12. Don't bother me until it's there. So the computer didn't have to waste time finding its way around the tape. Another feature that I don't know if it's ever used, we certainly used it in development, was the ability to imagine that a short piece of this tape, maybe 100 feet, was a loop. So you could go, use 100 feet of it, loop around, come back with another 100 feet, and you would have 200 feet of tape. And this would be very useful in program development because you could have one reel of tape on the machine, which could have, I don't know, 20 users doing program development. They'd all have their own little loop. So if I got one, I would say to the tape, move to loop 6. Then it would move to loop 6, which was me. And then I could read and write the data in this little loop. It was almost if I had a little private 100-foot tape unit of my own. Whether that was ever used commercially, I don't know. It's built in, but whether it was ever applied in a commercial environment, I don't know. As I say, we also had this 4-inch tape drive, which is in fact, there's a picture, I don't think we've got it on here, but it's academic, but you can just imagine it was just very big, very heavy, very wide, and very useless. So we've got the system, overall system. We've got all these mag tapes hurtling this data backwards and forwards, and all the other functions like cards tape, getting cards on tape, getting tapes back on the card, printing out tapes onto a printer, punching paper tapes, doing all those things are all dealt with by these offline units. And all this processor unit in the middle has to do is to process data. So what it consisted of was, first of all, there were these 4 buffers that I spoke of. You could have as many buffers as you like, up to 4, 1 rack per buffer, and they would connect with the tape system and read data into the memory and take data out of the memory and write it to the tapes. The arithmetic unit, like the 1100, used a 36-bit word. We had a decision to make at the time about bits and bytes and characters and whatever, and we decided to go for characters rather than bytes. And so we made the whole unit based around a 36-bit parallel word. The whole thing was a parallel machine. It's based on a 36-bit word, which was held in, everything was around that. That word could be either a binary number or 6 alphanumeric characters which you could send off to a printer. I'll come back to that in a minute. It was a 2-address system. One address, the main address, was this magnetic core store, which was 36 bits plus 1 parity bit, 37 bits wide, and ranged in size from a minimum of 4,000 words to, I thought, the maximum of 16, but I think I've learned later that it might have been 64,000 words. And you could just buy as much as you want and the power supply rack went on the end and fed all this lot. The cycle time of that was about 15 microseconds or so. So if you were doing a 2-address order, and everything was in here, you'd have to get one word out. As David said, write it back so you haven't lost it, go somewhere else and get another word, get that out and write it all back. So we had a second memory here, which was a small, fast memory. The Williams tube was around, mercury delay lines were around, but we decided that we didn't want any of that, so we built a thing called a diode capacitor store. And effectively what a diode capacitor store does is you have one capacitor for each bit, you charge it up when you want it to store a 1, you discharge it when you want it to store a 0. There were 64 words of that, and that was 38 bits wide. Now the problem with it is, you charge it up, you get all this information in it, in these capacitors. Then the capacitors do two things. They leak through their own internal leakage, and they leak through the back resistance of the diode that fed them. I don't know how long they would store the information for, maybe a quarter of a second. Then you'd have to go back and refresh it, read it all out, write it all back again. So there was this function that the processor had to do, which was to go around the diode capacitor store every quarter of a second or whenever it timed out and charge it all up again. But the reward was that you had a store with a cycle time of 4 microseconds. It seemed awfully slow these days, but when you listen to David talking about, 360 microseconds to chug this thing through, we do tend to take speed for granted now and think that perhaps this was old hat, but 15 microseconds on this and 4 microseconds on that, and a sort of a nominal 1 microsecond clock rate inside the computer was pretty good going in 1955. So there were 64 words of that in there, 36-bit words, plus a parity bit for checking, plus one more. The reason we had one more is that this was fabricated in bit pairs. So you could have 36 or 38, but you couldn't have 37. So we thought, what are we going to do with this 38th bit? So we decided we would make it a program switch. So this 38th bit of the memory became a program switch, of which there were 64. And program switches are jolly useful for when you want to go through a program and you want to keep track of things. You can set a little switch. Set switch 17 says to me as a programmer, I've done this, I've done all that bit, and I must remember to switch it off later on. So there were 36 data bits, 1 parity bit, and 1 switch bit, with a cycle time of 4 microseconds. So an instruction would take one number from there, one number from there, add, subtract, multiply, divide, all those other things, and put the answer back either in there or in there. And all the input-output went to the memory. So there was like a direct route, not direct as such, but from here to there. This arithmetic unit was pretty ordinary arithmetic unit in that it did what you'd expect an arithmetic unit to do, namely arithmetic. It added, it subtracted, it was to the complement, it multiplied, it divided, and it converted binary to decimal and decimal to binary. It also had a disarming effect, which David mentioned but didn't actually specify, which we didn't find out until a customer found it, which is that when you divide one number by another, there are actually 2 answers. Some of you may know this, but a lot of you don't. If you divide 20 by 3, you can either have 6 remainder 2, or you can have 7 remainder minus 1, both of which are legal answers. So we built this thing, and the trouble is when you have negative divisors, there is a tendency for the thing to give you the wrong answer. Empty and I point.
Right answer, I think.
What?
The different
a different right answer, a different right answer. Quite right, Dennis. This is my colleague who helped me design it. It's a right answer, but it's not the one that everybody wants. I didn't even realise until there were 2 answers. Nor do I understand to this day why MP&I, the Ministry of Pension and National Insurance, are dividing anything by a negative number. If anybody knows the answer to that, I'd quite like to know. Anyway, so that was what the arithmetic unit did. It was a 36-bit parallel adder, and as David was pointing out, the problem basically with a big adder like that is you've got to get this carry chunking up from one end to the other. And in a lazy world, you say, what's the longest it's going to take? And that might be 20 microseconds, and that's how long you wait every time you use the adder. we decided we didn't want to do that, so we had a carry complete circuit, which detected that whatever the carry was, however far it had gone, it had finished. Either a 0 had come out the other end or a 1 had come out the other end, but it was complete. That meant that if you only had to do 2 or 3 stages, if you like, increasing the binary number 7 to 8, you had 3 carries and then it would stop. And we had a circuit that detected all that, so that the addition, this bit of the operation was basically asynchronously operated. It hadn't got a clock thumping away. Each operation, when it completed, set off the next one. Nominally, sort of, I suppose you would say the tick rate was about a microsecond compared with the 1100 where it was 10 microseconds. But there wasn't a clock slaving away saying you must do this. And one of the ways we got around the long carry problem with the 36-bit thing was to do a carry detect. The way we got around it on the next machine, the 3400, which has been alluded to, was to design a much better carry system that only took a very brief amount of time, even if it was a full-length carry. So this was the arithmetic unit, and that was the arithmetic, and that was all pretty straightforward stuff, much as you would expect to find. But there were 2 features of this whole processor, which I think were, they're not novel now, but I think they were very novel at the time. First thing is this: if this is going to be a data processing system, the expectation is that this thing is going to be grinding away on data. So this data, when it's not grinding away doing sums, there's going to be data flowing into and out of these buffers. And the technique at the time on most computers was, you went probably on the 1100, you went, as Mike said, you gave one command which said read me a block off this tape. And for aught that I know, the computer sat there until that block was in, and then it carried on processing. If you do that here, you can only have one thing going at a time, whereas you might want, there's no point in having 4 buffers if you're going to do that. So we said, well, what we'll do is we'll have an instruction that says read 1 block from tape unit that's connected to buffer number 1. And then we'll carry on doing, we'll set that going, and then we'll carry on doing some processing on some data that we've collected earlier. Which is okay, but you then got to work out that the tape then starts up and the switching unit brings it through, and this buffer, one of these buffers starts to fill up. And you then have to, at some point, stop processing and get the data from here into there. So we had a thing called a breakpoint routine, which periodically, basically, between every instruction, would complete the instruction, and the next instruction in the program, it would say, the breakpoint mechanism would say, do any of you want servicing? Are you getting near to full up? Are you full? You've got a 2-word buffer in each, 2-word store in each buffer. Do you need servicing? One of them say, yes, I need servicing. So you just stop the program momentarily, go to here, find an address for buffer number 1, which pointed to somewhere in here, and suck in the 2 words of data from this buffer, put it into there, and this would then carry on reading tape, and you would carry on programming. So the input-output was in parallel with the program. So the program was carrying on, and it was interrupted by this input-output. But if you think about it, if you've got 4 tapes going at 20,000 characters a second, and they're all going fast, 80,000 characters a second. But this is a word buffer, and the word mechanism is a transfer. The transfer mechanism transfers a word. So you reduce that by 6 from 80,000 characters a second to 13,000 words a second, which is 70 microseconds a word. Now that's an awful long time to be hung up doing no programming, when in 70 microseconds you can take 2 words out of here, load them into the memory in 30 microseconds, and have the other 40 microseconds left to do all your programming. And that is if you've got all 4 buffers going flat out. So we found that magazines that were talking about, because there weren't a lot of computer magazines at that time, really, compared with now. In fact, there weren't a lot of computers. I think somebody calculated, I read something quite novel a few years ago, that said in 1950, which is 5 years prior to this, the total computing power in the world was less than a singing Christmas card that you give to somebody. birthday card for somebody. Because there was nothing. If you look through the computer archaeology and websites, there appears to be a lot of computing going on. There are a lot, maybe 100, 200 machines. But they're all experiments. There's nothing heavyweight in production, you know, doing real computing in 1950. Now, 5 years later, we're now looking into this. And we're doing the whole of this advanced technology and all transistor and the state-of-the-art machine is against that context. That 5 years earlier, in 1950, there'd be all in the country as far as computing in the world, as far as computing is concerned. So parallel input-output, which we probably now take for granted, was a very, very new thing in those days. But it meant that you were halfway through a program and you thought, I'm going to want some more data in a minute, so I'll send this command off. But meanwhile, I'll carry on processing this. And you could have 4 instructions. You could have 4 tapes whirring away in parallel with this data flowing into and out of the memory while you were going away computing on something else. And I think that was quite a sharp thing to do. And the other main feature of this was what's called a program interrupt system. On conventional computers at that time, you might have a series of indicators saying burglar alarm's gone off, fire alarm's gone off, I've got a parity error, somebody's tried to divide by 0, and they were just little switches. And from time to time, the supervisor, programmer, or whatever would look at these switches and say, has any of you got anything to say? Of course, most of the time they didn't. So you wasted a lot of time asking questions of these switches. So we said, well, there was this theory around that you could do it a different way by actually using any condition or any event which might be worth notifying to cause a program interrupt. That is, that the idea is that you've got a program running, something happens, you just stop it where it is, and you freeze it, and you go off somewhere else. You go to a known definite point in the store memory where there's another program that looks at these indicators and says, what are you telling me? Are you telling me you've got a power chain? Are you telling me you've got all this? But if there was nothing to say, you didn't waste any time doing it. And when it had finished it and dealt with it, which may be no more than telling an operator that something's happened, that the tape has completed a rewinding exercise, or telling the computer that some unit which they'd asked to be loaded up with the tape has now been loaded up with the tape. Because when the computer says to the operator through the console, put real number 433 onto tape unit 10, I mean, that could take quarter an hour, couldn't it? You've got to go in and go find 433, real one, find it, pick it up, go and find tape unit 10. Remember, I showed you the size of the computer room. You've got to find tape unit 10. There might still be a tape on it, so you've got to take that off, put it down, remember where it came from and why, what number it's got, put the new one back on, push it, thread it all round, rewind it all. So that could take a quarter of an hour. So when you've done it, you've then got to tell the computer who asked for it to be done that it's been done. So this might cause, I don't know exactly how, this might cause an event which would then be signalled to the software, and the software would say, what's up? Oh, tape unit 25, tape unit 10 is now ready for action. And set the little switch, maybe one of these, switches in the die capacitor store, and then the program in due time would look at that switch and say, okay, I'm now ready to read on that tape. And this program interrupt system, it's one of those funny things, program interrupts, that as soon as you float the idea, everybody in the design team produces a different reason why it can't possibly work. That's actually why I also said, well, you know, you can't because, but in the end, someone said, well, hang on, supposing, and then the supposings went round, and the number of, a bit like 12 Angry Men, you know, the number of objections went down, and in the end we built it in, and it worked perfectly, it worked very well. It's a good thing. But I bet there weren't many machines coming out in 1956, now parallel input output and program interruption. But we did. Now, because it was all transistor, it was very, very reliable, and John Bradbury, who was the field engineer, and Laurie Lawrence, who was also the field engineer, said they never really had any trouble with this. It was all transistor, it was cool, it didn't overheat. The big problem they did have was with these scramble bins on the tape units, but that was almost to be expected. What have we got now? Now, this is a different view of the, remember the first camera angle of the shot was from over here. This one is taken from over here. We don't know what these are. They look as if they might be power units, judging by the fact they've got these ventilating grills in the top of the door. This is the console, the operating console, which I'm going to talk about. And here we've got the processing unit. There's the spring going off the back, which is the core store, 2 racks. And then there's ROM. That's the die capacitor store. There are then 3 units of the arithmetic unit. There's a spring going off there, which is the core store. And then there's no, 1, 2, 3, 4. Counting the step. Okay, that's right. No, that's a rack. Right? So I said to Dennis the other day, I've got a problem. I can only have 4 buffers, but I've got 1, 2, 3, 4, 5 units. He said, well, I think it must be the power supply. Then there's a dummy unit there connecting. There's the magnetic core memory, 2 units going backwards. 1, 2, 3 units of the magnet of the arithmetic unit. Die capacitor store going back there, 2 more units here. So the entire processor set up for 4 buffers would just about fit in here. This piece here. Just, but you might not be able to get the doors of the racks open. This unit here, I don't know, could be anything. Search unit, input unit, what?
I think it's a switching unit.
You think that's a switching unit? Well, that one's a switching unit.
I think so.
Okay, very good. And there you can just see the edge of the tape unit with the scramble being empty because there's no tape on that hub. This console, very much like the 1100 console, had 36 lights and 36 switches. You could program, you could put instructions, coded instructions on the switches. You could put those in. You could run the program or you could stop it and single step it. You could do 1 instruction at a time and switch. There's a Cree teleprinter over here. There's a little tape reader and tape punches attached for program development. And there was also a variation of the ICT Samastronic, which we developed for our own development purposes. We also discovered that there was a way that you could fit an output printer, typewriter, a freedom flexor writer actually, for sending messages to the operator, which we had on the development machine, but there's no sign of one here, so I don't know if they didn't bother with one in Newcastle.
They had one.
They
had one there. They had one at each console, an output device.
You mean each console? Were there 2 of them at Newcastle?
Yeah, two computers now.
Okay. They need to learn.
You learn something new every day.
No. I learned enough from Laurie when I last spoke about them. Anyway, so, but there was as I said, there was no keyboard input. And I'll just finish off another couple of things. I don't know anything about the software tool we had. As Mike said, we could feed in binary coded instructions. We had a machine code assembly language compiler written by Dennis Pearson.
Sam Barton, I think.
Was it Sam Barton? Somebody wrote a machine language. So you could feed in the symbolic language and it would compile it all. The magazines, the literature of the time, the sales manual mentioned something about a compiler language, but I don't know what that was, whether it was what Mike was saying earlier about Algol. But I wouldn't have liked to write an Algol compiler in 64,000 words of store. But, that said, we did actually, when we got this into production, it was then taken over by others. The design team then went on to do something else, to design the successor. And for that, we wrote a design automation system to help design this new machine, which we did. And we got this design automation system programmed into whatever we had, 16,000 words. And oddly enough, as Mike said, we were all called in one day and told that we'd been sold to ICT. In the event, they didn't take the successor machine because they didn't want to add to what had been already described. Their catalogue was described as the largest range of incompatible computing equipment in the world. They didn't want to add to that, so they dumped that and used us to design the 1900. Now, the 1903 problem was that we were told towards the end of 1963 that we had to design it, and they wanted to go on the exhibition at Olympia, Business Efficiency Exhibition, which was in October 1964. We had about a year or just over a year to do it. So Brian Proctor and I designed the processor, and we thought, well, how are we going to, if only we had design automation. And so we rang EMI and said, do you mind if we come down and use your 2400? And they said, yeah, but you can't come down during the day because we're doing other things with it. But you can come down at night. So we used to go down at about 7 o'clock, run down to Steve Higgson here, and on this 2400 ran this design automation system, which undoubtedly speeded up the design time of the 1903, probably I would say by 2 weeks. That is in the context, you have to take that in the context of the fact that come the exhibition in October 1964, Brian Proctor and I, who were area-asked engineers, had to put on suits and drive the machine at the exhibition because they hadn't got time to train the sales operators who were going to operate the system. So Brian Proctor and I actually did it. And I think that was how close the 1903 came to not being demonstrable. And one of the reasons was that we ran this design automation system. So I think that's probably, was there any more? No? No? That's it. Back to run.
Okay. So Keith told us all about the 2400. While that was being developed, there was another NRDC initiative, and the EMI got another contract. So just to tell you what the NRDC were looking for in their fast computer project. So in 1956, the NRDC became concerned about the UK becoming dependent on American supercomputers. This was particularly for the national atomic energy programs and the atomic weapons programs. There were several American developments like IBM Stretch on the go. So NRDC started a fast computer project in 1956. They got several proposals and there was lots of discussions over a long period that went on for about 3 years. The initial proposal was for a design by Strachey himself to be built by NRDC. Sort of subcontract and build it themselves, but that was quickly realised to get industry involved, so moved on to 2 proposals, 2 quite different designs. One was being championed by Strachey and the NRDC, and one was being championed by Williams and his team at Manchester University. And eventually NRDC decided in June of '59, sort of civil service type, how do you decide on 2 competing projects, to place a contract with both, splitting the funding between the two projects. The EMI project was to be designed by EMI and Strachey. Strachey would have design control, and that became the 34,000 project. They got 2/3 of the cost that EMI asked for, and that was £250,000 at the time. The Ferranti project, that was designed and was already being developed in Manchester. It was the Muse system, which later became Atlas, and Ferranti got 1/3 of the cost they asked for. They got 300,000. So anyway, that's the sort of overall background. Say a bit more about the 3400 itself. There was a design. The design was to start from the sort of 2400 and use the latest technologies, design a new fast CPU, incorporate some of the new programming features that were being put forward by Strachey for this processing, and to initially was proposed to have a large store using some new magnetic film storage technology. But by the time the contract was awarded in '59, the target specification had sort of reduced a bit. EMI only got part of the funding they requested, and then they seemed reluctant to put in their own money into the project. They weren't having much success selling the 2400s, which, although marvellous, was over budget and late, and NRDC funding didn't actually bring any customers, so from a business point of view, a bit of a challenge. Sorry. on the 3400 project, the CPU was built. The film storage didn't turn out to work quite as well and wasn't pursued. The design continued. The one aspect that sort of surprises me is Keith told us about some of the overlapping and early time-sharing facilities that were implemented, and there's little evidence that we can find of there having been much design work done on that, but perhaps other people in the audience will know more about that and can comment later. Anyway, the project seems to have changed in line with the EMI business plans, but a team was kept together, and one of the interesting documents from the time is, that document's here. That was the front of a design specification document. You can see the Emidec 3400 is, sorry, 3400 is crossed out, Emidec 4, but actually inside the description is for a smaller machine which was being talked of as an 1100 replacement. Not long after EMI pulled out of the computer business, ICT bought the computer division, and there were changes at the NRDC. At NRDC, the promoters, Halsbury and Strachey, left in '59, and NRDC became less involved with technical innovation. At EMI, the computer division was bought by ICT, as has been mentioned, in July '62. ICT really needed to get an up-to-date range of computers to avoid being wiped out in its basic data processing marketplace by the IBM 1401. And as Keith says, ICT had a mixed bag of products. What it did was it rebadged the 1100s and became the ICT 1101. It kept the 3400 project going while it worked out what to do, and moved the whole team up to Stevenage. And then the frantic merger. The frantic merger occurred in 1963, and the attraction for ICT was the Franti FP6000 computer, which was an advanced multi-programming system that was already working. So ICT developed that into the 1900 range, and with large and small models. The small models were developed at Stevenage, and as Keith says, the EMI team moved on to the 1900 development work, and having that team of people who were used to working on advanced computers really enabled the small 1900 models to be developed quickly and got into volume manufacture quickly. So on that note about that the EMI team were key to that outstanding success in the small 1900s, I'll end on that positive note.
Put your hands up.
Thank you, Alan. We have now a discussion. Who would wish to ask the first question or make the first point?
Could you briefly recap on the dates, because some of the things that we've been hearing about overlapped in time.
Yes.
And indeed there were really 4 projects, including the very first one. Could you summarise the dates when each project, as it were, started and when the first one was delivered to a customer?
I doubt I'll get that right, but basically while the
407 being the first one in the list.
Yes, then the 1100s,
yes.
That was really one stream of development. Then a completely separate stream of development for the 2400.
Yes.
And shortly after that was kicked off, the NRDC started looking around at the fast computer, and then proposals were being considered for the for what became the 3400. I don't think I'll get the dates right if I try and explain more, but that's the sort of logic.
Perhaps an email would suffice.
Yes, yes. Yes, well, and there's a point actually in terms of the write-up of the history of these EMI machines. Simon's Our Computer Heritage project needs to have more put in it on exactly that sort of information. So some of the EMI people here today would welcome providing more information.
Alan, I've been discussing with you, Alan. I'm sort of intrigued to know a bit more about work and expand on it. And what was called time sharing on the 2400, which I understood at one time that Strachey had something to do with it, and that and Keith described the buffering system and the interrupt system, but there was obviously this paper that showed it, some concept of that being user, just potentially usable as some early form of multi-program.
It's not very clear, and it's not very clear as to whether this was proposals for the later machine or actually what was being done in the 2400 at the time. We really need somebody who knows what went on in the 2400 software.
My feeling was in the 2400 you could only actually load one program at a time. There was no facility for partitioning or protecting them from each other.
It was autonomous.
It would have to be, the program could have lots of different processes in it, which could be brought in by the program interrupt system.
Yes.
But it would be essentially one program.
If I can drag my own memories back, I remember reading Strachey's paper, and my recollection is it was really about interrupts. It wasn't what the word time sharing was then used in a different context later by the MIT people to have multiple users. And in fact, we in England called it multi-access, we didn't call it time sharing. The Americans called it time sharing, and I think that's the confusion. And Strachey's paper was really about interrupts and sharing the processor between running a program and controlling peripherals. That's my recollection.
Yeah, it certainly wasn't time sharing.
That's right. Multiple access was really a long way away.
But no, I wasn't even suggesting.
No, okay.
I was talking about what later we call multi-program.
Indeed.
There was a later stream of development which fed into what became the multi-programming in the 1900s.
Again, my recollection is that multi-programming came with Atlas. Atlas people took the time-sharing concept and implemented multi-programming, having several user programs running at once. Because they were talking about a job shop environment, whereas at Jumi 9 we're talking about, of course, big applications for data processing and so on. That's my recollection.
No, I think the first multi-programming came in with the small computer, the Orion.
Did it?
Yes. We had an original program inside it. I think it was about 128 words, which separated the programs. Each program was loaded in separately, and whenever it tried to use a peripheral that was busy or hadn't finished...
Orion and Atlas were in fact essentially
contemporary, yes. And a lot of the information went from Orion to Atlas and back.
And I think this really happened after what we've been hearing about
This was 1959.
That's right.
I remember the date.
Any more?
David, could I make a couple of comments, if I may? David Parsons, I'm on the Committee of the North West Group. Just wanted to give an update on one of the things that Michael said. In fact, this isn't the first time we've had the CCS have had a talk on the Emidecs. It's the fourth time. I gave one here in 2001 in this very room, and I've given two to the Manchester group, including a very detailed one on the architecture and how it was programmed and so on and so forth. But I thought I'd just mention one or two things. If any of you can confirm that Lloyd's Bank actually used an Emidec, I'd be very interested, because in the banking environment, they had this reputation that if it came from IBM, it was okay. We were, in Barclays, we were criticised for going to IBM for our reader sorters. But we had two machines, and one of them was quite, well, it was unique, because as far as I know, it was the only Emidec machine that had two IBM 7330 tape units as peripherals. And we had to have those in banking so that we could actually read the direct input from the check reader sorters off the new clearing systems. But one of the things that I'm sure if I mention it now, Michael will remember, where Michael, it was the loudspeaker on the console.
Oh, yes.
Because all the instructions when they were executed actually were audio monitored and played through a loudspeaker and had a volume control. And one of the things that we used to do, this is anecdotally on this if you'll allow me, David, at the Barclays Computer Centre, which was in Drummond Street, just near Euston, 154 Drummond Street, the place is still there, occupied by Logica, was that as a duty programmer, I used to get the telephone on the console permanently dialed to my extension in my programmer office through to a loudspeaker telephone so that I could sit there at night in my office and actually listen to the machine. And then I could go and tell the operators if there was something going wrong with it. And those, you remember that? Some of you who worked on it, we're really quite good at that. But one of my hobbies is music. And I got some music programs from EMI, do you remember? And we actually did a whole suite of music programs which were originally recorded by the BBC, but I've failed to find them in their sound archive. But I remember they used to regularly play at Christmas, some of the Christmas carols. Remember that?
Christmas party.
Yep, absolutely. Well, the other thing I would just mention is that the Barclays system is being written up in incredible detail by Ian Martin. Are you here, Ian? Ian is a Barclays colleague from many years ago who now works for the Open University, and he's doing a doctorate at Manchester in their Centre for the History of Medicine, Technology and so on and so forth. And he's taking as one of his case studies a very, very detailed history of the early use of computers in Barclays. And there will be a fairly substantial paper on the subject which might be of interest. I think particularly, Simon, it might be of interest for your archive. So maybe I'll talk to you offline about some of that stuff. But thank you, David. I thought it might just be worth making a few comments like that.
David Robertson.
Yes, just following what you were saying, I had a little bit of fun one week programming music on the 1100. I think I must be the first person ever to have done it. I think it was a Bury by Handel, but it was rather a lot of work coding it.
Absolutely.
And the real problem, the real challenge was coping with the rests in the music.
There are, of course, many stories about computer sounds.
Yes.
I'm going to tell you mine. The EdSec2 in Cambridge had a loudspeaker, and it made a characteristic noise according to the program it was running. And one day we had a visit from the post office. They said something around here is radiating on so many megacycles. And indeed, it was disrupting BBC television. And indeed, one of our users, who was a fellow at King's College, was sitting in his college room one night and saw the interference on his set. He said, "That's the EdSec2 test program." And he was right. Yes. Yes.
There, sorry, Alan Wakefield. This is a non-technical question, an observation, really. You mentioned Lord Halsbury and as a senior member of EMI, but so was Sir John Wall, who you remember came back and chaired ICL after being to the post office. Yeah? He was maybe not involved in that in the program.
A flippant point, but I did enjoy hearing the Samastronic mentioned twice without the usual swear words.
I know that too. So,
well, actually, just on the Samastronic, I was with EMI on the service side about 59. I have to say, I bought my first house on the overtime I earned working. But just quickly on that, music's been mentioned a couple of times as somebody who was just a mere engineer. The view we had was that the demise of our beloved EMI and all the opportunities we saw was caused actually by the Beatles. Because the view we took, a couple of things going on. At that time, someone mentioned Sir John Wall. The Beatles and groups like that were emerging. EMI was had the rights making millions of pounds, and the interest was definitely waning. And the senior sales manager around that time, a chap named John Glover, I think a number of people remember him, he had a big proposal in, the company Grapevine told us this, into Barclays for 17 Emidecs. He had a proposal in, we didn't win the business. As we understood it, had we got that order, we would have gone from strength to strength, perhaps the merger would have taken place, but we lost that business, which I think was a crossroads, as the rumour came back to us, the Grapevine, and Sir John Wall, all those up there, so we're not really going too far, lost the interest, let's sell it on to someone who wanted a real computer system in their army, which was ICT, and it all happened from there. So the Beatles and Barclays,
Yep.
we always held responsible for EMI computers biting the dust, as it were.
Just a point of interest. The first machine to be delivered was one we call P2, prototype 2, and that went to Glaxo's.
Did?
Boots might have had the first production machine, but Glaxo's had the first Emidec. Just as
One last point, I was actually in that first film. Unfortunately, you didn't see me, because I was sitting in the lorry. Took that big box up to Nottingham.
You mentioned the trouble with the Sanastronic printer. A terrible way to attempt to print anything on paper, but I do have a printout over there on the table showing how bad its print was when it was out of adjustment, and it actually is a printout of pi calculated to several thousand places, which is one thing which I did overnight.
I remember that.
At the time.
I remember that.
You remember that, yes.
Yeah, lots of water on the bridges.
A lot of talk about Christopher Straight, of course, a lot of involvement. I personally knew Christopher very well after this time we're talking about. He stopped being a consultant and came to Cambridge to work. And I'm in all sorts of dilemmas about Christopher in this project, because he was a brilliant man. I mean, there's no doubt about it, absolutely brilliant. He was much more of a scientist, I think, than an engineer. But my experience of him was he never actually finished much. Because scientists don't. The scientists go on to something else before they finish it, because they have another bright idea. It's engineers get it done. And I'm just wondering whether that had a negative effect on some of his developments in EMI all those years ago. Because he was quite mesmerising, Christopher. He was a very bright man, and he would be captivated anyone, including, of course, Halsbury. But he moved on, and I think perhaps that was possibly a good thing. But I don't want to malign the guy, because I knew him extremely well, and he did an awful lot for me personally. I'd like to make another comment. What I've learned today is that it makes me think of a possible theory almost about the history of British computers. That when we produce something very advanced, really beyond the state of the art, which clearly the 2400 was compared with the 1100, you don't sell many. When Ferrante produced something very advanced called the Atlas, they didn't sell many. And the theory I'm just developing on the spot is because the customers were nervous of them. They were, of course, very expensive, but they didn't trust them. They wanted something simpler. Indeed, the atomic weapons place, who had an Atlas II thrust upon them, actually wanted a stretch. And I'm wondering whether that's a common problem we had in those days, with 2400 on the one hand and the Atlas on the other. The interesting thing about it is, you said today that the 2400 sold three machines.
Yeah.
Do you know how many Atlases were sold? 3.
5.
How many Atlas IIs were sold? 3.
5 2400.
Sorry?
5 2400.
Yeah, okay, but it's the same order.
No,
the magnitude.
3 different orders.
Well, there were 6 Atlases there, come on. But it's interesting, isn't it, I think, that these advanced machines we produced, the bigger ones following the ones that were successful, were just too complicated for the customers to be prepared to buy. I'm sure they worked, but I don't think the customers trusted us. So.
I think the point relevant to that is that the 2400, or the pair of them that went to the Ministry of Pensions and National Insurance, ran the very first graduated pension scheme, and nothing else would have done that.
Right. I'm not trying to malign it. I'm trying to sort of make the point that by us all being too clever at the time, you just didn't replicate the volume of sales or the profits or anything. Of course they worked and they were brilliant. Hamish.
I think there's another part of that point is the difference between American management attitude and British management attitude.
Yes.
American management always want to be the sexy ones who've got the latest thing. And British management want to be second in the queue on using something that they know is going to.
But the Americans didn't want to buy British either.
The physical design of 2400 took account of the fact that we didn't have to sell many.
Yeah.
Because we used a small number of designs for the small printed circuit boards we plugged in. And the complexity of the logic was done in the back wiring. Right. So we had a relatively small number of separate boards, which meant you had fewer spares and your manufacturing was shorter. With the 1100, I think, it was on big. All the boards were different. And they could sell a lot.
We've got to 5 o'clock, so one last question.
Just on your point you just made, in the late 1960s, ICL kept trying to design a top-end machine for the 1900 range called 1908 or 1908A, and they all got cancelled because nobody wanted them.
That's right. Thank you. Can we finish? Can I say thank you very much to my alumni and the other ones. It's been a fascinating talk. I've learned an awful lot I just didn't know. Thank you very much. I have to tell you what's next. Our meeting in March is the 12th of March, and we have David Link, who in spite of his rather Anglican name is a German, and he's going to talk about the archaeology of very early algorithms, including Christopher Strachey's love letters. Then on the 23rd of April, we have Janet for the first 25 years, Janet of the network. And finally, for the season, on the 14th of May, which is our AGM, we have the BBC Doomsday Project, where we hope to repeat the success of the BBC Micro project we had last year. Thank you all for coming. See you next month.